And obviously, we talked about how to draw Lewis structures, and you want to make sure that you follow those rules. Again, a reminder that you do want to kind of single bond out of the box. You don't really want double bond or triple bond or anything like that. And that usually should get you a pretty good structure if you follow those rules. So, continuing on here with what we've been talking about, this is bond length, and you do not have to memorize any of these numbers or anything like that. But what we can see if we look at the trend here between, say, a single bond, double bond, or triple bond, if we look at the carbon-carbon single bond, it's 154. The carbon-carbon double bond, 133, and triple bond, 120. When we look at the carbon-nitrogen single bond, 143 distance, 138 the distance in a double bond, and in a triple bond, we see 116. What we actually see here is every time that we put a bond on, from, say, a single bond to a double bond to a triple bond, because we're moving the electrons between those two atoms, the positive nucleus are going to be attracted, and the distance between the atoms gets smaller and smaller as we put a double bond and a triple bond on. So typically speaking, when you have a single bond, that is the longest bond that you'll have. If you have the same sort of atoms in the bond and you make it a double bond, it'll get smaller, the distance between them, and even smaller as you make a triple bond. That relates to strength, the strength of a bond. A triple bond is actually the strongest, followed by a double bond. And the weakest of those three bonds, single, double, or triple, is actually the single bond, is the weakest of all of them. It's not like a double bond is like twice as strong as a single bond or anything like that, but that's the general trend that you see. I think of it like this: if you get like a brand new pencil out of the box, right, it's nice and long, right, big distance, you could take that and you could break it pretty easily. If you take like a chemistry test and all you got left is like the eraser and a little nubbin of the pencil, if you try to break that little guy, it's just super hard to do that, right? Because everything is so close together. And that's sort of what happens with our bonds here. As those electrons move in the center of the two atoms and brings everybody closer, everything's held a lot tighter, and it takes a lot more energy to break those guys apart. Any questions on that there? Now, resonance structures, we sort of touched upon as we were talking about drawing Lewis structures, but resonance structures oftentimes occur when we do have an option of, for example, making a double bond like we saw at different sort of locations. And because those double bond electrons are delocalized, they're moving around, like we saw in carbonate, at any given point in time, really those double bond electrons could be at any of those oxygens, which allows us to draw different Lewis structures, showing the double bond, for example, in the different locations. We do use these arrow here to indicate that they are resonance structures. So some of the ones that we took a look at earlier are, here's ozone as an example of that. You don't have to worry about the pluses or the minuses there, but ozone looks like this. And you can have a double bond there on the left. You also can have a double bond on the right here. And again, those are two resonance structures of each other. Again, those double bond electrons are really moving from one spot to the next. Bless you. The idea here is really, because those electrons are moving, the true Lewis structure is probably somewhere between those two pictures. So that allows us to draw more than one Lewis structure to indicate the bonding that's happening. Here's our carbonate one that we looked at earlier. It just has the charges on the oxygen. But again, pretty much if you need to draw a resonance structure, you're just going to move the double bond to all the possible possibilities, and you could draw again a new Lewis structure for each of those. The benzene ring, by the way, which is the guy on the bottom, I'll draw it towards the top, is actually a 6-carbon ring, and it actually has 3 double bonds in it. Each of these sort of points are carbons, and you could draw a resonance structure for that by just moving the double bonds around. And sometimes you'll even see benzene drawn like this with a circle in the middle to indicate that those electrons are kind of moving around and they could be at any location along the way. Other than that, you probably won't see benzene until you get to organic chemistry, but it's a very popular thing that you draw in organic chemistry. All right, so we'll skip that guy here, I think. Get the idea. All right, although in this class, everything that we will draw will obey the octet rule. There are a few exceptions to the octet rule that you do need to know, although you will not be asked to draw any of the exceptions. So everything that we do here will obey that octet rule of 8. The first exception to the octet rule is what's known as an incomplete octet. And an incomplete octet, much like the name implies, is there are certain things that are perfectly fine with less than 8 electrons. For the most part, that is beryllium, that is boron, and aluminum. Out of those three, probably the most common incomplete octet is boron. And boron, like the guy down on the bottom there, I'll draw it up towards the top so it'll be easier to see. When we look at the boron here in the center, it has 2, 4, 6 electrons only, and it's perfectly happy being that way. It's okay. It actually makes it quite reactive because it wants to actually get to 8. So it's actually something that you'll learn in 1B. That's what's known as a Lewis acid. It will, I'm sorry, I would say Lewis acid. It will basically accept some electrons because it's electron deficient. So they're quite reactive because they do want to kind of complete the octet. So they'll react with other things to sort of gain electrons. But boron, for the most part, will be okay. Beryllium here, hydride also only has 4, which is okay for it. But I would say probably boron is the most common incomplete octet that you see. 2 other types of exceptions to the octet rule is an odd number of electrons, like NO and NO2. So because they have an odd number of electrons, what happens is one of those electrons is all by itself, not paired up. And that is sometimes referred to, you maybe heard of free radicals. Yeah. And they're sometimes referred to as free radicals. They are also very, very reactive because they have one unpaired electron. So they're trying to kind of fix that. So they're very, very reactive because of that. Now, in atmospheric chemistry, where there's a lot of chlorine, it does that a lot. But when you get an odd number of electrons, you will have this unpaired electron. And again, that will result in something that's fairly, very reactive. Probably for your chemistry career, the most common exception to the octet rule that you will come across, which is again not in here, is the expanded octet. And there are certain elements that can go over 8 electrons, and it can have upwards of 10 to 12 electrons around them, and they're perfectly happy to do so. And that's an expanded octet. Like SF6 that we see down there, basically, if we just sketch the Lewis structure, not putting in all the dots on the fluorines, if we look at the sulfur, it has 2, 4, 6, 8, 10, 12 electrons around it, and it's perfectly okay doing that. When can that happen? If you look at the periodic table where sulfur is located, and you go to the right, you go to the left, and you go down where it is located. Those are the guys that have the ability to go over 8. That is because sulfur on the periodic table is period number 3. And if you remember, period number 3 on the periodic table is the 3rd energy level. What orbitals are on the 3rd energy level? There are S's, right? There are P's. And it's the 3rd energy level that we first start to see what orbitals? We first start to see our d orbitals, right, occur. And because they have these d orbitals available to them, even though they may not use them, they have a place to put the extra electrons. So that's why they're able to pretty much go above 8 and can. And again, sulfur to the right, left, and down where the nonmetals are will have that ability to go over 8. That means, though, if you look at the periodic table on period 2, where we have like nitrogen, oxygen, fluorine, and so forth, these guys are on period number 2, which is N equals 2. That means they only have s orbitals and p orbitals available to them. They do not have the d orbitals, so they can never, ever go over 8, no matter what the situation is. So those guys in that second period on the periodic table can never go over 8 because they don't have anywhere to put them. But starting at sulfur, right, left, and down, they do have that ability to go over 8. Once again, in this class, everything that you draw will obey the octet rule. You should not go over 8 in this class. That also means you should not Google your answers, because you will see sometimes some things drawn in the expanded octet with a lot more bonds. And then obviously I'll know you Googled it, because you shouldn't have that picture on there. Yeah. So make sure that you keep to the octet rule. When you get to 1A, you'll have plenty of practice with over 8s. Yeah, they do it a lot in 1A. But for here, we're going to keep everything obeying the octet rule. But these 3 exceptions are 3 that you should know. Again, you won't be asked to draw them, but you need to know what the 3 sort of exceptions to the octet rule are. Again, a incomplete octet, less than 8, an odd number of electrons, an unpaired electron basically, and more than 8, the expanded octet. Any questions on that there? So we're now going to talk about geometry, and this geometry is how the molecule and electrons are arranged. We're going to talk about 2 types of geometry. We're going to talk about electron pair geometry. And I'm just going to abbreviate that as EG for our lecture here. And we also will have molecular geometry. That is also sometimes referred to as just the shape. And I'm just going to abbreviate this as MG. So what we will see here, these are 2 names that describe the geometry. And it is electron pair geometry, how the electrons are arranged in 3-dimensional space around the central atom. And the molecular geometry is the overall molecule as a whole, how its overall shape ends up with all its bonds happening in there. So let's talk a little bit about the idea here. Molecular geometry refers to, as I mentioned, the 3-dimensional space. You can't really predict it from a Lewis structure, but you can predict it based on your Lewis structure and your central atom. So whenever we do geometry, definitely when there's 3 or more atoms involved, it's always the guy in the middle that is the most important. So that's always the one that you want to look at, is the guy in the middle. The basis of this approach is that we basically have valence electrons, which are negatively charged, which means when you get electrons near each other, do they really want to be near each other if they're both negatively charged? They don't. But they can't escape because they're involved in like bonds and stuff, and they're in there. So what ends up happening is, because they really don't want to be near each other, they will do their very best to get as far away as possible from each other. And if you think about it, as the electrons start to move, and there's atoms attached to those electrons, right, in a bond, those atoms are going to start to move. And that's going to affect the overall shape of the molecule as these electrons try to get away from each other. Everybody's going to kind of move with the electrons in some cases. And that's going to cause some different shapes that we see in terms of the geometry of these particular structures. This is known as VSEPR, which stands for Valence Shell Electron Pair Repulsion Model. And that is a mouthful there. But basically, when we do geometry, there's going to be 2 types of molecules that we will see. There are ones where you look at the central atom, and there are no lone pairs, no dots, basically. No non-bonding electrons. So they all have bonds, basically. The other type of molecule is one where there are dots or lone pairs, non-bonding electrons on the central atom, so you'll have some dots. And depending on whether or not you have sort of non-bonding electrons there or not, will affect the geometry names. Either they will be the same names for both of those geometries, or they will be different names depending on what's there. Now, probably the most important rule when you are doing geometry, and only when you're doing geometry, is this. If you have a single bond, a double bond, a triple bond, does not matter which one you have there, they all count as a single electron pair and also a single bond. So when you're doing geometry, it doesn't really matter what's there. Like I said, it could be a single bond, double bond, triple bond. These are the two things that you typically want to count when you're trying to do geometry. You want to know how many electron pairs there are and how many bonds. And pretty much everything counts as one. So if you're not doing geometry, obviously you count bonds like normal. But when you're doing geometry, everybody counts as one. And that is because they are effectively moving together. So even there's a double bond or triple bond, all those electrons are kind of moving together and they'll end up at the same shape. The second rule on the very bottom is not so important, but we talked about you could draw a resonance structure sometimes, which gives you different looking Lewis structures. You could do this geometry to each of those Lewis structures, and you pretty much will end up with the exact same geometry, regardless of Lewis structure. So if we did the geometry for the 3 carbonate structures we drew, we would end up with the same geometry for all 3 of them. So they'll basically end up the same geometry. All right, so let's get into really this. Let's start with, frankly, the absolute simplest geometry that you could figure out, and that is when you have a diatomic molecule. Because it's diatomic, there frankly is only 2 things there. And the only way you can arrange 2 things is in a straight line, right? Shortest distance between 2 points is a straight line. So whenever you have 2 things together in a diatomic molecule, the geometry is always linear, basically a straight line. It does not matter if it's single bonded, like we saw with F2. Does not matter if it's double bonded, like an oxygen. Doesn't matter if it's triple bonded, like a nitrogen. Doesn't matter if it's the same elements or different elements. All of those guys are just 2 atoms, and the only geometry you could have for it is linear, basically a straight line. Any questions on that there? Now, if that was how everything was, that would be great, but of course it's chemistry, so it's not like that. So when we get into 3 or more atoms, you have to look at the central atom, and you have to look at 2 things, the number of electron pairs like we talked about, and the number of bonds. So those are the 2 things you have to look at. So let's take a look at some of those. So this is our first example here. And again, when we look at this guy, which is an incomplete octet, for example, these are the 2 things that you want to look at. You first want to always, 3 or more things, look at the central atom. That is the only thing that's important when you're doing geometry. And we want to look at the total number of electron pairs. It doesn't matter if they're dots, it doesn't matter if they're lines. Again, everything counts as 1, which means we have 1 electron pair there and 2 electron pairs there. Now, something with 2 electron pairs, the electron pair geometry name, which is that EG, the electron pair geometry name, is going to also be linear. They're going to try to get as far away from each other as possible, basically opposite ends, and it will end up in a linear arrangement. The number of bonds that we have is going to be 1 bond and 2 bonds. So because these are bonded atoms, what ends up happening is as those electrons start to move, the atoms that are bonded to them move with them. So the atoms end up on the opposite sides of each other as well. And that gives us a molecular geometry name of linear as well. They will actually end up being about 180 degrees away from each other. So they'll end up with a bond angle of 180 degrees. both the electron pair geometry name is linear and the molecular geometry name is also linear as well. Any questions on that one there? Let's take a look at the next geometry, which is something like this, where we have three things attached to the central atom. Once again, we're going to look at the central atom, and in terms of electron pairs, we have 1, 2, and 3 electron pairs. Something with 3 electron pairs, the electron geometry name is known as trigonal planar, or sometimes referred to as triangular. So what happens is, in this case, the number of bonds, 1 bond, 2 bonds, 3 bonds, has 3 bonds. Again, because there's atoms attached, what ends up happening is, as those electrons move away from each other, the atoms are coming for the ride. But we now have 1 extra bond than we had before. So these guys try to get away from each other. These guys try to get away from each other. But these 2 guys on the bottom can't get too close to each other either, because they don't want to be near each other as well. And that gives us a molecular geometry name, also known as trigonal planar. That's because it makes, frankly, a triangle. That's how they get away from each other. It will make an equilateral triangle where the bond angle is 120 degrees. So we get a 120 degree bond angle on this. Again, basically spreading out enough that it makes like a triangle where everybody ends up. Yeah. You should know that. I think they want you to know the bond angles as well. So make sure you know the bond angles. Yeah. Other questions on that? The next example is something where we have 4 things attached, like here in methane. And when we look at the central atom, 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. Something with 4 electron pairs, the electron pair geometry name is known as tetrahedral. And again, because these are all bonds, 1 bond, 2 bonds, 3 bonds, 4 bonds happening here, the atoms will move with those electrons, and we will end up with a molecular geometry name also of tetrahedral. And it will create a bond angle of about 109.5 degrees. It basically makes like a triangle on the face and almost like a pyramid on the bottom. The same thing sort of happening here with that 4th bond in play. These guys got to stay away from each other. These guys got to stay away from each other. These guys and these guys got to keep some distance. So again, they're going to kind of keep moving around until they hit this kind of tetrahedral arrangement. Any questions on that? Yeah. EG is the electron pair geometry name. MG is the molecular geometry name, or the shape of it. Okay. Now, up until this point, both the electron pair geometry name, which I'm being abbreviating as EG, and the molecular geometry name, which I've been using as MG, they are different names or the same names? They've been the same names. And the reason they've been the same names is when you look at your Lewis structure, there's no dots on the central atom. That means there's no non-bonding electrons. So all the electrons that are there are bonding electrons. So as those electrons move, because they have an atom bonded with it, the atoms move with it. So the overall shape of the molecule and the electron pair geometry are going to always be the same if you have no dots on the central atom, because they're all bonding electrons. It is only when we start to introduce non-bonding electrons that we start to see a difference in the name, and the difference in the name is actually only the molecular geometry name will change. So the electron pair geometry will still be the same, and that's based on how many electron pairs you have. But because we now will have less bonds and more non-bonding electrons, it allows the molecule to get even further away from each other. And that creates a different overall shape for the molecule because of those non-bonding electrons. And part of that reason is the degree of how much electrons can be near each other. So the best case scenario is what we were just talking about, which is bonding electrons near bonding, so lines near lines. That's sort of okay. The next worst case scenario is non-bonding electrons near bonding electrons, so dots near lines in your Lewis structure. The worst case scenario that happens is where we have non-bonding electrons near non-bonding electrons. Those electrons do not want to be anywhere near each other, and because they do not have any bonds involved, they're able to really spread out and get away from each other, and that causes some pretty extreme shapes to occur. So let's take a look at some of these here when we get some non-bonding electrons involved. So if we draw sulfur dioxide, it will look something like this, which I think we drew earlier. And once again here, we're going to focus on the central atom. We want electron pairs. How many electron pairs does the central atom have? It has 1, doesn't matter if they're dots or lines, 2, and our double bond should count as only 1 more. So there are 3 electron pairs. The electron pair geometry name does not change. So earlier we saw something with 3 electron pairs. That is a trigonal planar geometry. But in this case, we only have 1 bond, 2 bonds. So because we only have 2 bonds, what ends up happening is these non-bonding electrons go upwards, and those guys that are involved in bonds go, I'm going to get away from you as far as possible, but then these guys, again, can't get too close to each other. And what ends up happening is we end up with a molecular geometry of what I'm going to call angular. Some people might call this bent angular, and some people might just call it bent. So we're going to roll with angular for this one. The bond angle on this one is going to be less than 120 degrees. That bond angle is based on 3 electron pairs, like we saw in that 120 degrees. Is less than 120 degrees because there's these non-bonding electrons. So it's able to kind of get away a little bit more, and it's going to cause the shape and the bond angle to change just a little bit less than 120 degrees like we had when we had 3 bonds happening there. Any questions on that one there? Next geometry is one where you have a central atom here like in ammonia, where you have 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. Once again, something with 4 electron pairs, the electron geometry does not change. So like we saw earlier, 4 electron pairs is tetrahedral. Now in terms of bonds in this case, 1 bond, 2 bonds, 3 bonds, we have 3 bonds. So something with 4 electron pairs and 3 bonds, we get kind of the same situation. The non-bonding electrons go up, keeping some distance from that hydrogens, but we have an extra hydrogen in there that also has to keep some distance between the other hydrogens as well. And it ends up with a molecular geometry known as trigonal pyramid. So trigonal pyramid or pyramidal is sometimes referred to. And it basically is that because it makes like a pyramid on the bottom and kind of a triangle towards the top in terms of its geometry. Now, taking this for a second, we saw trigonal pyramid here earlier with 3 electron pairs and 3 bonds. The molecular geometry for that guy is trigonal planar. They are different, yeah? And you do have to choose. Do not let me choose, because I will choose wrong with an X, yeah? So do not just write trigonal. And again, let me choose, because that's how I'm going to choose. That's with an X. So you do need to commit. Don't do my other favorite one, which is trigonal, very confident, P, very confident, in this kind of a line. Like, I think that line is planar, pyramid, something that line means, yeah. So again, they are different. You cannot just write trigonal. You got to either write trigonal planar or trigonal pyramid, depending on which one it is. Any questions on that there? Last geometry that you have is missing, apparently. Did I miss one? I did. It's gone. The last geometry that you have, let me do it here then, because apparently it went somewhere. By the way, the bond angle on this one, before we move off of it, is it's based off of this. It's less than 109.5. So less than 109.5 on this particular one. All right, I'm not sure where that last guy went, but let's do the last geometry here. The last geometry that you'll be responsible for is basically the one like we see in water. So if we draw water, looks like this. And when we look at the central atom, it has 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. Again, something with 4 electron pairs, the electron pair geometry is also still known as tetrahedral. In the case of water, we have all of the worst interactions you could have. We have bonding electrons near bonding electrons. We have non-bonding electrons near bonding electrons. And we have non-bonding electrons near non-bonding electrons, dots near dots. So because there is only 2 bonds in this case, the geometry here is, molecular geometry is bent or V-shaped. And what happens in this case is, frankly, those non-bonding electrons decide, I'm going this way, I'm going this way, I'm going to try to go as far away as possible. Unfortunately, they can't go too far because they're going to run into some hydrogens that are there. And these hydrogens on the bottom can't go too far either because they're going to run into each other. So they got to settle on this bent or V-shaped because it looks bent, or like an upside down V, basically, is the geometry that it makes. The bond angle here is less than 109.5. It's like 104-ish, in water is about what it's at. Ammonia is like 106 in terms of its bond angle, a little less than that. Any questions on that? So you do need to know the geometries here, both the electron pair geometry and the molecular geometry. Here's a table from your book, very similar to the one you have. You need to know the electron pair geometry. You need to know the bond angle and the molecular geometry as well. The best way to do it is, because most people cannot like memorize things 3-dimensionally in their head, myself included, is just to memorize it based off of a table, basically. How many electron pairs and how many bonds corresponds to what geometries. If you look up on Canvas, there is like a little thing that I made. It says like geometry and polarity. It has like a nice little table of electron pairs and bonds and talks a little bit about that geometry. Any questions on that there? Now, to finish up this chapter here, we're going to talk about molecular polarity. And molecular polarity is the entire molecule as a whole. Is it polar or nonpolar? And if it is nonpolar, what that means is, as a whole, all the electrons in the entire molecule are basically going to be shared equally. So what that means is you create really like a neutral molecule. There is no negative side. There's no positive side to that molecule. It's kind of neutral. The electrons are evenly distributed over the entire molecule. If you have a polar molecule, just like it means in a polar bond, you have a side to that molecule that's more negative, and you have a side that's more positive, because overall in that molecule, you have a side of it where all the electrons are kind of hanging out. And that's going to make that side of the molecule more negative and the other side more positive. In a polar molecule, they will have what is referred to as a dipole moment. Oddly, the dipole moment is the same arrow that we use for bond dipoles, where it points to the more negative side of the molecule, and this is the more positive side of the molecule. So we use that same sort of arrow to indicate dipole moments. Only polar molecules will have dipole moments. Again, nonpolar molecules will not. So let's talk a little bit about how we can determine if a molecule is polar or nonpolar. The easiest ones to determine whether or not the molecule is polar or nonpolar are diatomic molecules. And diatomic molecules are the only place where bond polarity, and if you're not sure what I'm talking about with bond polarity, that's when we did our difference in electronegativity values, right? And we're able to draw those little bond dipole arrows if they was polar. And molecular polarity will be the same. So for example, if I have H2, the bond here, right, between the two hydrogens, is it polar or nonpolar? It is nonpolar. Difference in electronegativity there going to be 0, basically, right? Now, because that is the only bond in the entire molecule, and it's nonpolar, this would make this a nonpolar molecule as well. And that's because there's only one bond and it's nonpolar, so the entire thing has to be a nonpolar molecule as well. Same thing if you did O2, doesn't matter if it's double bonded or single bonded, that is also a nonpolar bond. And because that is the only bond there, then that will be a nonpolar molecule as well. Same thing if we took something like HCl. Between hydrogen and chlorine, there's a difference in electronegativity that makes this a polar bond, where it is more electronegative on the chlorine. Now, that is the only bond that's present, which means that this would also be a polar molecule, where in this case, this arrow that I drew would represent the dipole moment that's happening here as it's pointing towards the chlorine. The chlorine is going to be more negative in that guy molecule than the hydrogen. That's the same thing as we had with HF as well. We have a polar bond, and that will also be its dipole moment, and it would be a polar molecule as well. So probably the easiest ones to figure out is the molecule polar or nonpolar is if you only have two elements involved, diatomic molecule. If that bond is polar, then the molecule will be polar, and if that bond is nonpolar, the molecule will be nonpolar. Any questions on that? So when you get, though, to 3 or more atoms involved, you have to look at two things. You have to look at are there polar bonds? And you also have to look at the molecular geometry, or the shape. So let's take the classic example of carbon dioxide that we drew earlier. When we look at the bond between carbon and oxygen, is it polar? The answer should be yes, because carbon and oxygen are in the same period on the periodic table, and they are not at the same spot. So we would have polar bonds heading in this direction. Now, because it has polar bonds, you may think to yourself that this molecule will be a polar molecule, but we do have to look at the molecular geometry. This central atom has how many electron pairs? It has 2 electron pairs when we're doing geometry, right? Stop drinking in here. Yeah, thank you. Now, in terms of bonds, it has 1 bond and 2 bonds, which are also the electron pairs, right? Which are 2. So something with 2 electron pairs and 2 bonds has a molecular geometry of linear, right? That's the guys can get 180 degrees apart from each other. Now, because the geometry of this guy is linear, these polar bonds will actually cancel each other out. It's like if my pen was the molecule and I pulled to the right the oxygen, and the oxygen on the other side is pulling to the left. I am actually pulling in opposite directions. My pen is going nowhere. They are canceling each other out, basically. So because of this geometry, this molecule is actually going to be nonpolar because it will cancel each other out. That is because those bond dipoles are vectors. They have direction and magnitude, I think I remember in physics. And in some cases, they will add to each other. And in other cases, they will cancel each other out. In this case, because they're going equal and opposite of each other, they will cancel each other out. Now, if you look at something like water, which also has polar bonds heading towards the oxygens, the geometry of this, as we just did a second ago, is 4 electron pairs and 2 bonds. That's going to be bent or V-shaped, which means that essentially you have like a sort of V happening. You have electron density coming this way and this way. Almost think of like they're meeting up on top like a string, and if you pull from the top, the whole thing's going to move. And it will have a net dipole moment heading in that direction. And this guy will be polar, where the oxygen side of water is more negative and the hydrogen side of water is more positive. And it will be a polar molecule with that sort of dipole moment happening through the oxygen here. This being more negative, this being more positive. So because these vectors add to each other, and it works something like this, kind of draw one going in that direction, one going in that direction, and then they combine heading in that direction. Frankly, nobody wants to draw vectors, right? So there must be an easier way. So there definitely is an easier way. So to finish up on here, the easiest way to do it is dots or no dots. So there are certain geometries which are symmetrical. And for you guys, you don't have very many. You have trigonal planar and you have tetrahedral. And these are the molecular geometries we're talking about. What all these guys have in common is when you draw the Lewis structure, there are no dots, non-bonding electrons on the central atom. And if you have that in all the outside atoms are the same, you will have a nonpolar molecule. And that is because everybody will basically end up symmetrically apart from each other, and they will all cancel out. Like if I take this guy, I draw my Lewis structure, and I look at the central atom, I see no dots, right? Everything on the outside is the same. There is polar bonds heading towards the fluorine. But because of its geometry, they're all going to pull equally. Like tug of war, if everybody pulls on the rope equally, they're going to cancel out. Nobody's going anywhere. And this would be a nonpolar molecule. Now, if I swap out a fluorine for a hydrogen, and I'm not drawing the dots on the fluorine for just purposes here, we still have polar bonds, but now with the carbon-hydrogen bond, that is a nonpolar bond. That's that 0.4 difference. So what we have in this case, though, now is everybody over here is pulling, right? And this guy is not doing much, right? He's just hanging onto the rope. So it's like if you have 3 people pulling on one end of the rope, right, and just one guy hanging on, he's going to be dragged across, right? And it will now become a polar molecule. So if you have a geometry where you draw a Lewis structure and you look at the central atom, there's no dots. Everybody on the outside is the same element. Pretty safe bet to say nonpolar molecule. If you draw a Lewis structure, no dots on the central atom, and everybody on the outside is not the same element, pretty safe bet to write polar molecule. That leaves us unsymmetrical geometries, which for you guys is our angular, our trigonal pyramid, and our bent or V-shaped. And again, these are molecular geometries. What all these have in common are there are dots, are lone pairs on the central atom. And if you have dots on the central atom and all the outside atoms are the same, it's going to be a polar molecule, most likely. That leaves you really only linear that you have to worry about. Linear is pretty easy to understand. It's a straight line. So if you have, like we had in CO2, where they're heading opposites of each other, that will cancel each other out. If you have linear, where the dipoles are heading towards each other, they will also cancel out. It's like two people on opposite sides of the door pushing equally, right? Door's never going to open. But you could have a linear where everybody, in terms of their dipoles, are heading in the same direction. Then it would be a polar molecule. So this is how you could do geometry really quick, like this, just real quick here, like this, right? This is really how quick you could do it. We look at this guy, there's dots, right? Everything on the outside is the same, polar or non-polar? Polar. We look at this guy, no dots. Everything on the outside is the same, right? Going to be non-polar. Yeah, just pretty as quick as you could almost do it. I look at this guy, no dots, but everything on the outside is not the same, right? So it's going to be polar. So that's as quick as you can do molecular polarity, dots or no dots, pretty much.